Good morning, everyone. Thank you very much that you are with us in one more Athena European University and Hellenic Mediterranean University Sci Cafe colloquia talk. On behalf of the organization committee, Professor George Kavulakis and Professor Georgios Kavulakis, I would like to also welcome you and thank you. It's a great pleasure that we have today with us another distinguished scientist, and this is Assistant Professor Jovana Milic from the University of Freiburg in Switzerland. Few words about Jovana, Professor Milic, if I pronounce well. Right now she's a group leader at the University of Freiburg in Switzerland, but before this she has done her PhD in chemistry in 1988 in Zurich. In 2017 she has spent postdoctoral time in EPFL under Professor Michael Gratzel, who was our first speaker in this colloquial talk. Her research interests, among others, and more related to today's talk, is like supramolecular materials for energy conversion with particular focus in photovoltaics. Today's talk is like supramolecular strategies in hybrid perovskite photovoltaics. Her work has received more than 2,000 citations, and we are very happy to have with us Jovana in today's colloquial talk session. So Jovana, the floor is yours. And once again, on behalf of the organization committee, thank you. Ευχαριστώ πολύ in Greek. All right, thank you.
Well, thank you very much for this kind introduction. And thank you for the invitation. It is a real pleasure to be here and contribute to this wonderful initiative. I am about to share my screen, which should hopefully be visible at the moment.
It is.
In full screen.
In full screen.
Wonderful. Well, thank you once more. I really appreciate it. And it is further my pleasure also to share with you today some insights and broader overview of the role of different supramolecular strategies in controlling hybrid perovskite materials with a particular focus on applications in photovoltaics. Now, this required a highly interdisciplinary and collaborative effort over the past few years, which also motivates me to, before I proceed, highlight and thank all the colleagues and collaborators who have in different capacities contributed to this work. Those at, for instance, the Adolf Merkel Institute of the University of Freiburg, where I am presently based, leading the Smart Energy Materials Group with the generous support of the Swiss National Science Foundation, a number of other financial agencies, but more importantly, our international collaborators, including some of those highlighted here that have contributed to the work that I'm going to outline, being those at the Max Planck Institute for Solid State Research in Stuttgart, University of Tübingen in Germany, AMOF in the Netherlands, and EPFL in Switzerland, with whom I remain affiliated, where I especially want to highlight and thank the ongoing support of Professor Michael Gratzel, whom we already have the chance to hear from, not only in the scope of our collaborative efforts, but also ongoing mentorship and support in the process of establishing an independent team, but also with our ongoing collaboration. I further like to thank a number of colleagues in the groups of Professor Lyndon Emsley for their support with solid-state NMR spectroscopy, Professor Ursula Rötschelsberger for theoretical insights, and Professor Jacques Moser for advanced photophysics characterization. Well, I am incredibly fortunate to have the chance to work within such an interdisciplinary team of colleagues that also share the enthusiasm for this research direction, which essentially evolves along the objectives of controlling complex molecular assemblies in order to address a specific functionality at the molecular, material, and ultimately operational device level, with the purpose of further developing smarter materials and technologies that can respond to different external stimuli and adapt to their operating conditions. Now, the inspiration for this work often comes from natural systems, as nature is even though not perhaps as effective often as our artificial technologies, it is much more adaptive in this regard. And here, supramolecular strategies play an important role in controlling different biological processes, such as those of, for instance, natural photosynthesis, which has in fact inspired the development of a number of artificial technologies for energy conversion, as those in photovoltaics, as illustrated here by this dye-sensitized solar cell that maybe most closely mimics these natural systems through molecular photovoltaics approaches pioneered by Professor Michael Gretzel. Now, however, unlike natural systems, and in particular these artificial photovoltaic technologies mimicking them where solar to electric energy conversion is exploited, in natural systems, these photoinduced electron transfer cascades are often used to produce chemical energy, which involves the role of specific components known as molecular machines, such as the here illustrated ATP synthase that stands alongside other powerful biological machineries comprised of these functional assemblies of molecular components that are at the core of the energy conversion process, stimulating the development of a number of artificial analogs or molecular machineries that operate under comparable principles of tailoring now different non-covalent interactions between the functional components in order to address a specific function at the molecular level, which has been at the core of my research pursuits, evolving along these questions of whether we can truly repurpose these bio-inspired supramolecular tools in order to address some of the challenges associated with artificial technologies for energy conversion as those in photovoltaics. And this becomes especially relevant with the new generation of photovoltaic technologies, including those of hybrid perovskite solar cells, which have attracted considerable attention over the past decade. And already, even though emerging only over a little bit more than 10 years, over the last few years, they have already surpassed the performances of some of the market leaders, including, for instance, polycrystalline silicon, while at the same time offering a much more advantageous technologies in the sense of their cost effectiveness, thin film preparation, and also solution processability that contributes to this ongoing interest in the photovoltaic research community. This is primarily related to the exceptional properties of the photoactive absorber layers, namely metal halide perovskite materials that are here schematically illustrated by their crystal structure, that are in these conventional solar cell architectures here schematically represented, normally sandwiched between different selective charge extraction layers, which can also be prepared relatively straightforwardly by solution processing, contributing further to the accessibility of these technologies, and which are represented by this schematically illustrated cubic crystal structure defined by the AMX3 formula, representing such divalent metal halide MX based corner-sharing octahedral framework that hosts smaller central acations that can be either inorganic species, such as cesium, or small organic molecules, like methylammonium or formamidinium, which renders these structures hybrid organic-inorganic materials. Now, of course, their remarkable properties in photovoltaics are absolutely fascinating and stimulate a lot of research interest, but what I find particularly appealing when it comes to these hybrid organic-inorganic materials is that these ionic and crystalline materials are at the same time dynamic and soft materials that also feature mixed ionic and electronic conductivity, as well as the capacity to adapt to a variety of dimensionalities that really provides a powerful platform for such function-driven material design and the possibility of developing smarter nanotechnologies. Now, while some of these attributes are further contributing to the appeal for the use of these materials in a variety of optoelectronic applications, they are unfortunately also related to one of their major challenges, which is in fact their limited stability, leading to their photovoltaic performances, as already outlined during the previous talks that you've had a chance to witness, are gradually decreasing over time, particularly when exposing these materials to external or environmental factors such as oxygen or moisture to which they react, or even due to the operational conditions where these systems are exposed to, such as temperature changes, voltage bias, or light, that stimulate ionic migrations within the active layer as well as the neighboring layers that further contribute to different degradation processes that are more intrinsic instabilities and that stimulate really an ongoing effort in the community to address this pressing issue. Now, in the face of this issue, over the past few years, we have aimed to address it and contributed to the cost by relying on a specific and rather unique toolbox in that regard in the form of, well, supramolecular chemistry, which is now here very schematically illustrated by this Swiss knife of different non-covalent interactions, such as hydrogen bonding that most of you are probably familiar with, other related interactions like halogen bonding, pi-based interactions, or others, whose now versatility, but also adaptiveness, enables the development of different functional materials, but also more adaptive or smarter nanotechnologies. And which is relevant in the context of hybrid perovskites, as it really permits tailoring these interactions between different complementary molecular components, but under under corresponding building blocks, such as by designing small organic molecules that can, for instance, interact with the surface of hybrid perovskite through different non-covalent interactions, direct their structure, and affect their properties at the molecular level that can then be translated into a functional device operation. Now, in terms of this function that affects the macroscopic properties, including the ultimate device operation, we could identify three key areas that are subject to such molecular modulations. And these are, for instance, morphology controls that are important for the operation of the active absorber layer, defect passivation involving the suppression of different defects that are responsible for the losses in performances, and ultimately enhancements of the stabilities that are either related to the extrinsic factors, being the environment, or the intrinsic operation-induced ion migration. Now, each of these functions can be translated now into a set of complementary supramolecular tools to address them, such as, for example, using hydrogen bonding to tailor the morphology of these materials, as illustrated here, for instance, cross-linking different perovskite phases or affecting their general structure, more indirectly affecting the resulting properties, but also affecting their optoelectronic characteristics, for example, by directing this octahedral connectivity that is directly affecting the optoelectronics, since it's defined by the metal halide orbital overlaps. Furthermore, using other, perhaps to an extent unconventional non-covalent interactions in this regard, such as halogen bonding or even pi-based interactions, to not only control morphologies, but also suppress specific defects, or furthermore, building self-assembled molecular layers that are highly hydrophobic based on, for instance, van der Waals interactions to increase the resilience against moisture, or suppress some of the ion migrations where, for instance, host gas complexation strategies are further advantageous. Now, to really demonstrate the proof of concept for relying on some of these approaches to address the present challenges and tailor the properties in these materials, over the past few years, we have looked into a number of tailored molecular components, some of which are illustrated here, that rely on different supramolecular interactions, from hydrogen bonding and metal coordination through pi templating effects, halogen bonding, different hydrophobic van der Waals assemblies, or since recently host gas complexation, each of which really demonstrating different capacities to tailor the properties and enhance the stabilities of these materials that are primarily related to these three general functional categories, such as the morphology controls, defect suppression, or a variety of mechanisms for stabilizing these systems, both extrinsically and intrinsically. Now, apart from focusing on these macroscopic properties and their role in the resulting device operation, which is very important, this has been possible by truly focusing on the atomic level interactions that enable this advanced molecular design, which was possible by complementing a number of conventional characterization techniques with the unique role of solid state NMR spectroscopy, particularly by looking into specific NMR active nuclei, such as carbon-13 or nitrogen-14 outlined here, to identify presence of new chemical environments that can be related to the appearance of new phases, especially by comparing the characteristics of the neat samples to those of the modulated ones, their role in the structural characteristics, or also ion binding capacities that could be directly related to the intrinsic stabilization of these systems. Now, apart from achieving this by using these small organic molecular modulators on the surface of hybrid perovskites, this opened the path to incorporating such organic moieties within the hybrid perovskite framework in order to build extended or lower dimensional perovskite systems, such as these layered two-dimensional perovskites, where now the organic component acts as a spacer layer, separating or templating inorganic or hybrid perovskite slabs, further directing their structures and the resulting optoelectronic properties and stabilities, which really highlights the importance of two particular considerations when it comes to the supramolecular control outlined in a more general sense over the past few minutes, including the role of different non-covalent interactions and their templating effect, which I hope to illustrate to you today by focusing on three relatively recent examples as case studies that highlight the role of different interactions, in particular halogen bonding and pi-based interactions, as well as host gas complexation. Now, when it comes to halogen bonding, this is a type of interaction that is that some of you might not be familiar with, which motivates me also to introduce it, as it is very closely related to hydrogen bonding, in the sense that it also takes place between a corresponding acceptor, which is a nucleophilic species, a highly electronegative atom like nitrogen or oxygen or halide in this case, and in this particular case, halogen bond donor, which is, unlike hydrogen, a highly polarizable halogen atom attached to an electron withdrawing core, which permits the formation of an area along this halogen carrying atom bond of relatively positive charge, illustrated here in blue, known as the sigma hole, which is the defining feature of halogen bonding in the sense that it also enables this interaction to be highly directional, taking place only within angles that are very close to 180 degrees, which is reflected in the design of a number of or selected representation of these halogen bonded molecular modulators, one of which I will use today as an example to illustrate the concept, being this, for instance, tetrafluorodioiodobenzene, or TFDIB, that involves this electron withdrawing perfluorinated benzene core equipped by two iodine substituents serving as halogen bond donors, sufficiently active to form the sigma hole for the halogen bonding interactions with the surface of hybrid perovskite, such as through the halide anion halogen bond acceptors. Now, apart from this structure directing role of the perfluorinated core, it has also been relevant in the context of increasing the hydrophobicity of these materials, hopefully contributing to their extrinsic stabilization, but also ion binding capacity through both halogen bonding and other interaction with the perfluorinated core, contributed to the intrinsic stabilization. In addition, fluorine in this case, especially when analyzing unconventional interactions in hybrid perovskite, is particularly advantageous as a potential label for as the highly sensitive fluorine NMR spectroscopy that helps identifying these modes of action. Now, in terms of these modes of interaction, based on the characteristics of halogen bonding, we could anticipate two types of interactions that these molecular species could feature in these materials, being either this schematically represented asymmetric binding mode through the surface of hybrid perovskite, or this symmetric binding mode cross-linking different perovskite phases, which are defined by this molecular axes separating the fluorine environments that are either inequivalent in the asymmetric binding mode or equivalent in the symmetric binding mode. Now, furthermore, this binding can take place through either these halide termini that I highlighted, which is in accordance with the directionality of halogen bonding, but also, and which will be in this case labeled by the index X, but also looking into the hydrogen bonding interactions that are more common in hybrid perovskite through this acation cavity surface. We can also imagine, or at least project, the possibility of having some of these analogous halogen bonding interaction, which will in this case be labeled by the index A. Now, in order to really assess the presence of any of these modes of actions in the resulting materials, they're commonly prepared by both solution processing, so conventional spin coating from the precursor solutions followed by annealing to form the corresponding films, or for higher quantities of materials, especially for solid-state NMR spectroscopy, we also conventionally use mechanosynthesis, where now the precursors are ground in a ball mill followed by annealing. In both cases, in case of the modulation, including some of the substoichiometric amounts, commonly in the range of 5 to 10 mole% of the corresponding modulator that is then assessed in the resulting material. Now, this assessment primarily involves, in this case, as already indicated, solid-state NMR spectroscopy, in this case, fluorine NMR spectroscopy of different precursors, illustrated here, and a variety of perovskite compositions, all of which indicating in the presence of the modulator, appearance of two particular species labeled here as 1 and 2, that are tentatively assigned to asymmetric and the symmetric binding mode. Now, to scrutinize these assignments and gain more confidence in their presence and existence, we complement this one-dimensional fluorine NMR spectroscopy with the two-dimensional NMR techniques, in this case, fluorine to fluorine spin diffusion experiments conducted in the group of Professor Lyndon Emsley, that essentially involve monitoring the exchange of the magnetization through space, through dipole-dipole interactions between the inequivalent fluorine nuclei that result in the appearance of these off-diagonal signals correlating to chemical environments on the corresponding axis, in this case present for the species 1, unlike species 2, where such correlations do not exist, suggesting that indeed species 1 can be ascribed to the asymmetric binding mode, while the species 2 corresponds to the symmetric binding mode. Now, having assigned these general binding modes on the surface of hybrid perovskites motivates us to further look into their specific orientation that involves a number of different configurations and stimulates complementing these NMR measurements with theoretical molecular dynamics calculations and DFT calculations of the corresponding chemical shifts in an approach otherwise known as NMR crystallography that enable us to confirm these original assignments, looking into hundreds of different configurations, but also exclude one of them being the symmetric binding mode through acation cavities, which is in line with the directionality of halogen bonding, and which is done within the level of confidence, including errors of both the density functional theory calculations and the NMR spectroscopy, offering us more insight now and confidence in the presence of halogen bonding and in the nature of these interactions in hybrid perovskite material. But at this point, one might wonder, how does these atomic level interactions really, especially these weak interactions, truly affect the macroscopic properties of these materials? Well, looking more carefully into their morphology, for instance, by scanning electron microscopy, we do not really see major changes in the morphology of these materials in presence of these relatively weak and substoichiometric amounts of the corresponding modulators, which is also reflected in the optoelectronic characteristics, which are not in any way compromised in presence of these modulators, in this case, in a conventional triple cation double halide perovskite composition. This is, in fact, also the case for the photovoltaic performances that are preserved for the control samples as compared to the control samples. So in presence of the modulators, we do not change the photovoltaic performances at all in these small quantities of modulators inside the perovskite composition or at the interface with the corresponding whole transport materials, for example. However, what we do see consistently is that despite these results in terms of the no major effect on the photovoltaic performances, the stabilities of these materials are consistently enhanced and illustrated here by one of the examples, monitoring the continuous operation of these solar cells by continuous irradiation, enhancement of the stability of the treated sample as compared to the control systems that was ascribed to both the hydrophobicity of these materials as well as the ion binding capacity related to the intrinsic stabilization. However, looking more closely into these ion migration properties and seeing a minor change in the activation energy for these halide migrations in presence of the modulator stimulated us to further look into these H sample, for example, looking for more insights into the modes of stabilizing the resulting materials, seeing in particular something interesting for the formamidinium-led halide-based materials, which are very appealing from the perspective of their optoelectronic characteristics, but which have this major challenge of being thermodynamically inaccessible at ambient conditions, under which they form this non-perovskite delta phase that is optically inactive, the so-called yellow phase, which reappears in the age samples that are not treated, unlike the age-treated samples where we do not see the appearance of this phase over the same time scale, suggesting that perhaps this modulator has a further effect on potentially altering the energetics of this transformation that is being currently further investigated. And generally highlighting the importance of considering a combination of contributing factors when it comes to using molecular modulations to control the stability of these materials. In general, I choose this example for the reason that these weak interactions illustrate another important feature of supramolecular chemistry and supramolecular control in general, is that despite these interactions being weak, they're multiple. And as a result, they can and will make the difference in the resulting materials worth further investigating. Now, this is relevant in the context of halogen bonding, but also other related interactions such as pi-based interactions that I would like to illustrate further, which are relevant in the context of these molecularly modulated samples, but even more so in lower dimensional or layered perovskite architectures, where now the organic component serves as a spacer layer templating the inorganic perovskite slabs in the manner that either involves this bifunctional organic monolayer with the well-aligned inorganic slabs in the so-called Dion-Jacobson or DJ perovskite architectures, or such monofunctional organic bilayers, characteristic for more common rootless than popper or RP architectures with a slight half a unit cell offset between the inorganic phases. In both cases now, the role of the organic material is even more important, as it not only templates the resulting hybrid structure, but the assembly of the organic component directly affect the structure and indirectly their optoelectronic characteristics, as well as the stabilities through both the hydrophobicity of the organic component as well as their ion impermeability, which we have analyzed over the past few years by looking into a number of different spacer components, which conventionally involve this typical butylammonium alkyl chain or phenylethylammonium based species, both corresponding to the rootless than popper phases, which we have extended in a number of other aromatic or carbocyclic systems, including adamantyl for van der Waals based interactions, or different types of small aromatic or extended aromatic units for, in particular, Dion-Jacobson architectures. Now, in this analysis of these variety of systems to control these organic assemblies, pi-based interactions were particularly relevant. And especially when attempting to control them by inverting the polarization of the benzene ring by perfluorinating it in order to access these more parallel rigidified organic assemblies controlling the properties of the resulting materials. To assess the possibility to achieve this, we have referred to two relatively simple model systems that involve this archetypical phenylethylammonium spacer or PEA, so small aromatic ring with an ethylene linker and the acation mimicking ammonium termini that binds to the inorganic slabs, and its perfluorinated analog here labeled as FEA. In fact, FEA-based systems have already demonstrated the capacity to not only form well-defined two-dimensional rootless and popper phases, but also contribute to stabilizing, for instance, formamidinium-rich lead halide or especially lead iodide compositions, as illustrated in one of our earlier collaborative efforts, where these two-dimensional materials were used as overlayer on the formamidinium lead iodide phases, leading to further enhancements in their performances by suppressing some of the defects, but more importantly, their long-term operational stabilities, even in humid environments, which was ascribed to primarily the hydrophobicity of this spacer group that is relevant for moisture resilience, but also achieving more appropriate contacts with the whole transporting materials. Now, using such a system in a one-to-one mixture with its non-fluorinated analog enables maintaining this stabilization factor, while at the same time further enhancing the performances of these materials in conventional solar cell architectures, here illustrated by this cross-section, where these two-dimensional overlayers were applied at the interface between the three-dimensional perovskite absorber and the corresponding whole transporting material, which was now associated with the capacity of these systems, despite the formation of these well-defined two-dimensional structures, maintain the resulting optoelectronic characteristics, so which are very beneficial and should not be compromised. And similarly, the three-dimensional perovskite structure despite the capacity of each of these systems, so the PEA, the non-fluorinated, the perfluorinated FEA, and their one-to-one mixture labeled as PF, to form this well-defined two-dimensional perovskite phase, as illustrated by this typically layered periodic X-ray diffraction patterns. Here, we need to start being careful in assessing their properties by solely relying on XRD, as this is primarily the result of the inorganic framework. So to really gain insight into the behavior of the organic components and their supramolecular assemblies in the spacer layer, we had to complement this analysis once more by solid-state NMR spectroscopy. In this case, by relying on the fluorine to carbon cross-polarization measurements that once more exploit these through space exchanges in magnetization through dipole-dipole interactions that are effective within the ranges of up to about 1 nanometers that can happen due to nanoscale proximity, such as by pi-pi interactions, resulting in this case in the fluorine to carbon cross-polarization NMR spectra in the appearances of these additional signals highlighted here in both the mixtures of neat spacers as well as the corresponding layered perovskite architectures, suggesting their presence in nanoscale proximity as desired. However, if we more critically assess these spectral characteristics, we also see that the comparison with the mixture, so the mixture of the two spacers to the one of purely perfluorinated system, features also very comparable spectral characteristics in this aromatic region, suggesting that perhaps this nanoscale proximity could be also the result of nanoscale segregation instead of a bulk alternating fluorinated, non-fluorinated system pi templating effect. And to scrutinize this more critically, we complement this analysis once more with NMR crystallography approach, looking into a number of different configurations, some of which are illustrated here, including this fully alternating layered system, including both aromatic and perfluorinated systems, checkerboard-like structures, or this kind of stripe-like assemblies, considering both twisted and parallel orientations of the corresponding spacers that are identified in their crystal structure, ultimately revealing a linear correlation between the calculated and the experimental data in case of the chemical shifts of both carbon and fluorine, with the closest match to the of the theoretical assembly to the experimental structure being the one of structure 1, this fully alternated system that is also found to be most thermodynamically stable. But in fact, the most accurate match within the accuracy of about 99.9% is the one that corresponds to the mixtures of neat phases, suggesting that indeed these systems, especially in thin films and mechanosynthetically prepared powders, are in fact nanosegregated, meaning that they preferably form alike structures in the films and mechanosynthetically prepared powders that remain at the nanoscale contact, leading to these cross-polarizations, which really challenges the previous reports and opens a broader perspective to the role of this pi templating in these materials. Importantly, this effect is also general in the sense that we observe the same behavior when moving from Rudess and Popper to the Iron-Jacobson architectures, where we see comparable nanosegregation occurring with these materials that further affect their affinity to hydration, for example. That is important, and it really challenges our perspective on the role of pi templating in advanced material design. Now, this is relevant for these layered perovskite architectures, but equally important when considering these other approaches that are more interfacial molecularly modulated treatments, which I would like to briefly come back to in my last example that involves the role of host-gas complexation. Now, this is a concept with a very long history in supramolecular chemistry, and it refers to the formation of such host-guest complexes between a pre-organized, commonly macrocyclic molecular host species and often smaller geometrically compatible guest moiety that can happen through different non-covalent interactions. Now, with this definition in mind, we could even argue that hybrid perovskites are, to an extent, host-gas complexes of an inorganic framework hosting different A cations. So it is really ubiquitous in both nature and material science, responsible for different biological processes, but also material or molecular functionalities, especially those in the field of different molecular machineries that I've been particularly invested in, as illustrated here by one of the examples of a molecular gripper that I've been dedicated to for many years, including this particular case that has been also designed by looking into the interactions within the photosynthetic reaction center that are now translated into the design of this molecular gripper system that can controllably expand and contract in response to different external stimuli, such as electric charge or light, leading it to reversibly release or capture smaller moieties, opening the perspective to its role in molecular sensing, delivery systems, nano receptors, or perhaps elements in nanorobotics. Now, inspired by some of these smart molecular systems stimulates further efforts to exploit these host gas complexation strategies in controlling the properties of other hybrid materials, such as hybrid perovskites, particularly in a functional device during operation, by controllably binding and delivering specific ions that are relevant to their operation. To demonstrate a proof of concept for this, over the past few years with our colleagues in the group of Professor Gretzel, we have looked into one of the relatively simple examples with the of a host moiety, otherwise known as crown eater, which is a very typical host system in supramolecular chemistry, here illustrated, more particularly, specifically in the case of this study, including this dibenzyl 24 crown 8 architecture that is selected on the basis of geometric compatibility with specific ions, but also the screening systematically of both aliphatic and aromatic analogs, with the purpose of interacting with specific ions at the interface of hybrid perovskites, especially those of under-coordinated lead cations and A cations, which, in case of using the system as a molecular modulator from an orthogonal solvent at the interface with whole transporting materials, led to remarkable improvements in performances associated with the suppression of some of the defects, but also operational stabilities related to directly this ion binding capacities, which were assessed by using once more solid state NMR spectroscopy, where the binding, for example, of the lead cations was assessed by both lead NMR experiments using combination of different precursors and the resulting modulated perovskite, as well as their heteronuclear correlations, in this case, correlating the chemical environments of the lead with those of the proton, especially of those of the crown ether, whose presence suggests their existence in the close nanoscale proximity that is relevant to demonstrate their binding capacity. Similarly, this was done with formamidinium cations by using carbon NMR spectroscopy, as well as, in this case, proton-to-proton spin diffusion experiments, correlating again the environments of the crown ether with those of the formamidinium cations, suggesting their presence in the nanoscale proximity and confirming their binding capacity that was also complemented by density functional theory calculations. Now, in this case, the capacity of this system to now competitively bind both metal and A cations enable it to be used as a molecular vehicle or a shuttle to deliver specific cations, in this case, cesium cations, within the hybrid perovskite architecture, especially those of the formamidinium lead iodide-based perovskites that, as you might remember from the earlier part of this talk, are not very easily thermodynamically accessible at ambient temperatures, but which can be stabilized through, in this case, a gradient of cesium cations that is leading to the further stabilization and improvements in the resulting performances of these materials, but more importantly, their operational stabilities, even at elevated temperatures, which highlights the importance of this, in this case, multimodal host gas complexation effect that relies on a synergy between the host now binding these competitively, these ions at the interface that act as defects and possible ion migration sites, its hydrophobicity, but also the cesium cations for this, as a gas stabilizing the resulting perovskite architecture and the resulting host gas complex delivering the effect. Now, in this case, apart from the beneficial photovoltaic effect and the stabilization of the resulting material that I would like to especially highlight, it is important to note that these systems illustrate a certain potential for increasing the sustainability of these materials, as when these solar cells are immersed in water, we see a substantial reduction in the release of lead ions, suggesting that some of such strategies could be used in reducing their negative environmental impact. Now, having demonstrated this for both molecularly modulated systems and layered hybrid perovskite architectures, stimulates further efforts to fully exploit this rich supramolecular toolbox to not only address the pressing challenges, but truly understand these effects at the atomic level and open a path to advancing these materials in the future, such as by, for instance, fully exploiting the utility of the organic component and introducing additional functionalities within the organic layer that is especially relevant in these extended layered perovskite architectures that are in fact commonly for typical spacer components that are electronically insulating, behaving as quantum wells, where the charges are primarily confined to the inorganic framework that defines the resulting optoelectronic properties that can be altered by tailoring carefully the organic component to access other quantum well structures where the organic component, that is in this case electroactive, further contributes to the process and stabilizes the system without compromising the resulting performances of the materials, which we have been very invested in, such as by using some of the electroactive spacers, as one illustrated here, based on naphthalene D imides or NDI moieties, extended to form and bifunctional to form Dion-Jacobson architectures, which have already illustrated the capacity to contribute to stabilizing some of the formamidinium layered hybrid perovskites that are also underrepresented, revealing by NMR the presence of these systems, stabilizing also the desired alpha phase, but importantly, showing the direct electronic exchange between the inorganic and the organic phase that is illustrated here by transient absorption spectroscopy, in particular by looking into different two-dimensional perovskite architectures, revealing the presence of this absorption between around 550 and 600 nanometers that directly corresponds to the formation of the NDI radical anion, as illustrated here in the meat spacer upon excitation at 400 nanometers that can photogenerate these stable radical anions that could not be accessed at higher wavelengths, for example, at around 510 nanometers, but were used, in fact, to excite the perovskite samples containing NDI, nonetheless showing the presence of radical anions that results, in this case, from the exchange between the inorganic and the organic phase, opening a path for more functional layered hybrid perovskites. These systems still face a number of challenges that need to be addressed for their application in photovoltaic devices and other optoelectronic functional systems, but they conceptually are opening an interesting path for further utility of layered hybrid perovskites, which apart from electroactive moieties, could involve further photoactive species that we have been very invested in, chiral moieties, or even mechanoresponsive, introducing additional physical stimuli to control their properties apart from electric charge or light, being pressure or the associated strain that we've been recently exploiting to demonstrate that, in fact, pressure can be used to reversibly control properties of layered perovskites as well, as illustrated by this example of tailoring their optical response that we very recently reported on, using pressures in the low pressure range up to around 0.35 gigapascals, that is comparable or induces a comparable strain to some of the internal chemical processes, and that is in that case relevant for not only understanding their effect, but opening the path for their further application, especially considering the reversibility of these processes. Well, and this importantly opens the path for these systems that go well beyond photovoltaics and towards smarter nanotechnology. Well, with that, being mindful of the time, I hope to have provided you with a broad overview of some of the capacities of these supramolecular strategies in tailoring these hybrid perovskite materials and through different noncovalent interactions and their templating effect, including halogen bonding, pi-based interactions, host-gas complexation, or the opportunities to enhance their functionalities, affecting the characteristics of the materials, but also their properties in photovoltaics, which now opens the path and stimulates further research in advancing their properties towards smarter nanotechnologies. With that, I wish to briefly thank once more all the colleagues and collaborators that have in different capacities contributed to this work and which are all diligently outlined in the references that I cite. thank you once more for their support. I'm really grateful to have the chance to work within such an interdisciplinary team of scientists who also enforce my belief in the necessity of the interdisciplinary collaborations when it comes to tackling some of the complex contemporary challenges. With that, I would like to finally thank you all for your kind attention, while I very much look forward to our discussion. Thank you.
Thank you very much, Jovana, for this very nice talk and your enthusiasm that, has been transferred to all of us without any problems with your voice. I have to say this. So if you can please stop sharing the screen and check the audience for any possible questions. I have some questions, but I'm a physicist, so mainly my questions are coming from the chemistry point of view. That I have a lot of gaps of knowledge. So I would like to give the floor. Oh, thank you very much. We have also Peter with us, Professor Bolivar. It's very nice that we have Peter with us as well. So any questions regarding to our speaker? You can type your question to the chat, or you can switch on your microphone and direct your question to Jovana. So before they will start, I have some questions, and from the very, excuse me for my ignorance on the questions that I will ask. First of all, I would like to I had an idea now after your talk. How do we define these supramolecular constructions? And then the next question that I have is how do we define soft materials? And also, I would like to give me a concrete example from the device point of view, how these kind of structures, the effect, for example, the stability, without these structures and with these structures, the performance with these structures and without the structures. Just give me, indicative numbers regarding the improvement, because this should be the motivation. A part of the functionality that's indeed is like a Legoland. You can do whatever you want. And Peter probably would like to include some of your ideas in our master degree, that this Legoland can perform and can build whatever we want. So the floor is yours, Jovana. And once again, I'm sorry for my questions, but they are coming from a gap of knowledge.
Thank you so much for your question. I mean, I have to, in that spirit, I will have to, in fact, excuse myself for my lack of knowledge in physics, perhaps. I think this is where this interdisciplinarity and complementarity come into place. And I'm already very happy that you started with I'm inspired to ask, because this is one of the ideas of sharing the knowledge and stimulating the inspiration. First question regarding the supramolecular chemistry, I would argue that even without highlighting that these systems are supramolecular, or using some of these unconventional noncovalent interactions that are already supramolecular, nearly everything is supramolecular when it comes to extended materials and systems. And what they are defined by primarily is these noncovalent interactions. So interactions that are not ionic or covalent bonds that form conventional materials and that involve these ranges of different non-covalent assemblies is the main criteria for defining these systems as supramolecular. This is where I have highlighted these hydrogen bonds, halogen bonds, and there are many others that play a role in their extended systems in solution, but also in the solid state that are emphasized here, and which are often more easier to identify in the solid state because they are much weaker in general. So many of the competing interactions with the solvents might interfere with identifying them in that regard. Now, follow up on how do they really play a role? Well, one of the why I'm so stimulated by supramolecular chemistry goes beyond this inspiration in nature that really illustrates greatly how the supramolecular interaction can play a great role, because they're much weaker than ionic or covalent forces, but their multiplicity really still plays an important role, like in examples that we're all very familiar with, including DNA and the reason why we are even able to then have this conversation. What is important here is I find them relevant for smart materials because they offer these components of reversibility, breaking and making the bonds in response to different external factors that opens the path to adaptability. Now, adaptability is then a factor that emerges from this that is very unique, but on the other hand, also error correction mechanisms that nature is much better at when we speak about the adaptability. I've been talking about adaptability more from the perspective of responsiveness and the ability to really reconfigure depending on the environmental inputs. So I hope that this maybe helps understand better what this really implies and what are these systems and why they're referred to as such. On the other hand, how does this now concretely affect the material or the device in particular? I think some of the examples could already give you a feeling because comparing some of these systems in presence and absence of some of these targeted now non-covalent interactions through these molecular modulators and their assemblies really show that we can increase the longevity of these materials. Now, this we already see on the material level before even introducing additional stimuli in the device operation, like voltage, now temperature changes or light. We already see if we leave these materials in open air for a long time or operate with them in a long time, presence of some of these moieties contribute greatly to increasing their stability. There are different mechanisms, and that's something that I was trying to emphasize because it's important to understand them before we argue how we can really proceed with this molecular design. One of them is definitely this hydrophobicity, because water is a big problem with these materials, and this can be incorporated in many different ways, and not only through these targeted non-covalent interactions. But more importantly, I would say their role is in controlling their intrinsic stabilization, primarily through ion migration. We see that many of these systems contribute to changing the activation energies for the migration of some of the critical ions. And this is, I believe, where adaptability is very important, because the conditions under which these systems are exposed also continuously change as the solar cell operates. And we know also that some of the ion migrations are reversible, while others are detrimental for the performances. So having a system that can adapt to this would be very critical and important, but without interfering with the main operation of the core material. So this is where I think is the most powerful factor for stabilizing their operation. In addition, they are important in general crystal engineering. So this is the basis. I have not maybe emphasized this enough, but overall crystal engineering, these changes of the morphology or even changing the preferential phase that forms, like with this form of vanadium lead iodide phases, is important. And this is maybe an area which requires more investigation in the sense of how does this real mechanism of formation by what are the intermediates that perhaps play a role? We are focused on the final product, final material, operation in a device, but in the process of forming them, what are the intermediates that play a role, which could be an important question to assess much deeper. So with other in situ measurements, especially structural, to understand. I hope that this covers most of the questions in a more general sense. Well, with the concrete examples, I hope that I try to deliberately not focus on the numbers, because I believe that there is an importance in looking into these systems more fundamentally. There is clearly an effect on both the performances and the stabilities, but I would like to advocate for more fundamentally understanding them to really open the path for controlling this more reliably.
Thank you very much, Giovanna. Thank you very much indeed. So now the floor to Professor Bolivar from University of Zigin. Peter, the floor is yours.
Thank you, Kostas, and thank you, Giovanna, for the really wonderful and exciting talk. Yeah, and the field is obviously fascinating in terms of all the possibilities which are opened up by the supramolecular structures. I have to excuse us, I will have to leave soon to another telco, but I'm fascinated by the possibilities and scared by the complexity. Yeah? Me being an electrical engineer who worked in conjugated polymers in the 90s, yeah? Many, especially of the electrical properties, at the end depend on the macroscopic ordering, which you promise to enhance via this design, but inducing additional distances and additional complexity due to intermediate molecules. Could you elaborate a bit how much are you already working on electrical properties, which will depend on the end on the long-term hopping transfer of excitations from molecule to molecule? And do you have an intuition of the loss of properties of conductivity, etc., yeah, by inducing an additional distance? Yeah, that would be one question. Yeah, and the other would be in this: is there any hope to be able to model the electrical properties? Yeah, which obviously it's it's modeling a lot of molecules and to be able to design the electrical properties. Yeah. And we are like trying to make now an electrically driven perovskite laser, yeah, which depends on optical properties, but on electrical transport and densities, etc. And so this is fascinating, scary, promising. Could you elaborate on electronics for an electrical engineer?
Thank you so much for this question and also the comment. I share the sentiment. As someone who has also transitioned from a different field, and clearly I have been nurturing this passion for supramolecular chemistry for a very long time before even discovering hybrid perovskites. It is worth commenting in general that we have to recognize that the entire field of hybrid perovskites, especially photovoltaics, is very young. It's really there only a bit more than a decade, and we are truly learning more about these systems at many different levels, not only molecular and structural, but device and electronic as well. In that sense, I also have a feeling that we started with something very complex, but then we are increasing the complexity in order to fully understand it and to even stabilize it. So I recognize this as an issue, but at the same time, I also recognize the perspective and the effect of occasionally increasing this complexity to actually simplify the system. So I think this is the trend where one is going, in fact, because in presence of some of these agents that now initially increase the complexity for us to really understand what's happening, we ultimately simplify the system in terms of the resulting phase. But also, even when we think about beyond going towards the electrical engineering and being able to study now these materials and functional devices, we are opening the perspective to simplifying the resulting architectures. If we think critically about some of these, for instance, layered structures, where we introduce additional contribution of the organic component, and we are increasing the complexity. But then if these systems provide the potential for selective charge transport, we can simplify the resulting architecture by removing some of the layers. And this is where the idea of currently maybe increasing the complexity would offer more simplicity in the future. Now, for the second part of the question, and considering this complexity and the role of the organic components in the electronic processes and transfer, they are really delicate at the moment because they are so far primarily electronically insulating, and this explains why most of these systems have been used in very thin layers just to facilitate some tunneling through the layers in order to be able to still extract the charges without compromising the resulting performances, but maintaining the stability of the system. This is what we're trying to challenge by introducing some of the electronically active or photoactive systems where we want materials to directly participate. And many of these studies are still actively ongoing. We try to analyze these systems in depth and their electronics and devices, but a lot of questions are still open in that regard. So for conventional systems, when we think about the role of this organic in the organic materials in the hybrid perovskite architectures, I can reassure you most of them do not really contribute to the electronics other than affecting or directing the structure and perhaps improving the context with the selective charge transport layers. Because otherwise they're, yes?
In PVs, in fact, you investigate the transport, the vertical transport, not the molecule, but the vertical.
Yes, but these systems are mostly layers at the interlayer with the selective charge transport layers, and they do have an effect. So in that sense, I would argue. On the other hand, when we now, it's important to understand that controlling, because these are very anisotropic systems, when we think about the extended layered systems, so this is where controlling their orientation is very important. Because if they are insulating, only certain orientation permits us extracting the charge. And I would argue this is the argument for having them transport charge as well, because for some of the systems where this is effectively done, we no longer have to think about the orientation, which is very difficult to control.
Okay, thank you very much.
So these are some of the aims. I hope it helps maybe translate, but I'll be happy to continue.
Thank you very much. And I'm really sorry. I would love to continue discussing, but I have to leave. Thank you very much.
On another occasion.
Giovanna, regarding what Peter has mentioned about electrically pumped, perovskite lasers. In this case, I think that the construction is not only, I mean, the construction and how these organic molecules they affect the electrical properties. It has to do how easy you inject, electrodes from the electrodes to the material, and not only this, I mean, in lasers, also you should take into account about the lifetime of the electrons as you inject them from the electrodes, you know, to the upper laser energy level. So also more studies, I think they have to do about how much, you know, this organic structure and the orientation, as you mentioned, affects this lifetime of the electrons on the upper laser state, no?
We know that, especially with these interfacial treatments, you have a major effect on the work function of these materials, and you then immediately affect the energetics of the contacts. So this is another way to tailor this. But of course, going into this direction, one has to take this into consideration. But at the same time, we can consider this only when understanding how they are structurally even assembled to see where we are altering this energy. But so all of these studies are complemented also with this with the analysis of the energetics to see whether we are really impeding on the charge extraction or we are facilitating it or not interfering in general.
Let's give the, you know, I can see the George Kakavelakis. George, the floor is yours.
Hello, Giovanna. Thanks a lot for the very nice and detailed presentation. I have a question regarding in one of your slides, I think number 43, you presented or you had a perovskite formula that was not exactly ABX3, but was AB 1.03, X 1.09, something like this. Is it this, I mean, alternation to the typical behavior, is it because of the supramolecular chemistry, and how this alternation affects the tolerance factor or the stability of these systems at room temperature?
So thank you, George, for this question. Indeed, this triple cation double halide composition had a slight excess of lead iodide. So the only reason why we use this particular composition is that it has been the most conventional one to use for this type of devices for comparison. So we wanted to see the effect in that composition. Now, your second part of the question, a quick answer in terms of whether now the supramolecular strategies have the effect or not. We always compare these systems to reference materials that do not have any treatment. And in that sense, we do definitely see the effect even in presence of these excess lead iodide. For many of these compositions, the small excess has actually been used to target the interaction with some of these materials, especially when you have these A-cation mimicking functions that could potentially form layered hybrid perovskites. So this has been one of the strategies in the community where you have a slight excess in order to form a coexisting two-dimensional phase, for example, for 2D, 3D heterostructures in these materials. So we have not used it for that purpose, especially because we have a halogen bonded system that does not form a layered structure because it cannot preserve it from the perspective of charge neutrality, but it does have an effect probably on how they bind. This is another reason why in this study where I report this this composition with slight excess of lead iodide, we also study the interaction with lead iodide itself. And we see that we still have these two symmetric and asymmetric phases with the lead iodide, modulated lead iodide itself. So we know that the modes of interaction will be comparable. I hope it helps maybe gauge the reasons why and what are the effects that we see.
Thanks a lot for the reply. And another, I mean, comment or question I have is, recently I have seen in a talk regarding the perovskite field effect transistors, they are using very similar 2D perovskite materials with large A-cations. So have you ever tried to use these supramolecular designs applied in similar vertical, I mean, devices, such as field effect transistors?
Thank you also for this question. I think so far we haven't been looking into transistors. I have to say, we have been extensively analyzing mixed conduction in these materials. That's why I speak about these effects on ionic migrations with more confidence, but this has not been done in any transistor configuration, but very simple model devices that are just two contact devices using, for example, galvanostatic classical polarization measurements that are galvanostatic, or complementing this with other conventional analysis in model systems and not a transistor-based configuration. But I could imagine seeing a variety of effects in these systems where the same questions were applied, right? Controlling the structure, morphology, and the assemblies before trying to interpret the electrical properties, right? But it's probably an exciting direction.
Ioana, you have already provided to us some material for our ministers, so it's a good example.
I'm happy to see you here, Kostas. Thank you so much. I wasn't sure if you will join, and I'm very excited about how these material or about the effects of these materials.
Yes, I will update you soon about the results.
Maybe I will be able to answer some of the questions on the transistor side as well.
Okay, yes.
Excellent, excellent.
I would say when it comes to transistors and these types of properties where changing these behaviors reversibly is pronounced with supramolecular systems, the advantages would be even greater, I would argue, especially when using this in the context of memory elements. So this is something to consider in the broader context, George, if this is maybe what inspired you to ask the question.
Okay, I think George is happy with the answer.
Mm-hmm.
All right, so I think that now we should close this session. We should thanks again, Giovanna, for this very nice talk. And we're going to renew our meeting in the Sai Cafe in 2 weeks' time, not next Friday, but the Friday after that. We're going to have another speaker from Switzerland, from EPFL, Kevin Sivula, that he's going to speak to us about semiconductor photoelectrodes and photocatalysis for solar-driven water splitting. So let's renew our meeting on the 2nd of December at 10 o'clock CET. And once again, Giovanna, thank you so much. And your voice was perfect.
Great. I mean, this is the only voice you hear now, so you don't realize the difference, but hopefully at some point. Thank you so much. I really appreciate it, and it was a pleasure to interact with you, and I hope this stimulates more interaction in the future.
Yeah, definitely. Thank you. Bye. Have a nice day.
Thank you. Have a good
Bye-bye.
day. Have a nice weekend. Bye.
Bye.